Hello everyone, welcome to lecture 33 of the course Diffusion in Solids. So, last two videos in this lecture, we first introduced the concept of CALPHAD approach, how it serves as an important tool to predict the phase equilibria and the kinetic simulations. And then last lecture we introduced some of the softwares that are useful in implementing this approach. Now, we also mentioned that one of the key component of this whole predictive capabilities is the database, because the database is something that provides the collection of the data based on which the models can be developed, and then they can be used to predict the behavior, and the reliability of the database directly impacts the quality of your predictions. So, let us start with that. So, we have what is database? Basically, it is an organized collection of data that allows for efficient access, management and updating. That is a very general definition of a database. And in computational modeling, when it comes to, it stores critical information derived from experiments and simulations. The accuracy, as I said, of the computational predictions directly depends upon the quality and the comprehensiveness of the database. The more comprehensive the data, better predictions you will be able to make. A good database is built upon the accurate experimental data, proper evaluation and optimization techniques, and consistency with the physical principle. So, all these are important to make a database reliable and a good database. The poor quality databases can lead to erroneous predictions or misleading insights for material designs and processes. Of course, we want our prediction to be as close to reality as possible, and the quality of the database is a key factor that decides that. Now, why the database is necessary? So, experimental data for material systems are scattered and inconsistent, because you see that in each domain there are researchers around the world who may be doing the experiments, evaluating different properties and so on. So, these data tend to be scattered. Sometimes you have some inconsistency also because of the experimental uncertainties and the deviations and so on. So, then the many modern design processes such as CALPHAD and kinetic simulations, they require your database as input. So, this enables the virtual experimentation. Why we are talking about this predictiveness is because we want to reduce the number of experiments that you need to do. So, let us say in a phase diagram, if I have a 0 to 100, the composition varies. I can in principle have infinite number of compositions. Okay. Let us say that for each 1% I am interested to know what are the phases, but that would require me to do 100 experiments. Can I do, for example, 10 key experiments, and then rest of it I can predict using a very good model. So that my number of experiments are now reduced from 100 to 10. So, this is what we mean by the virtual experimentation or the computational tools. That is the power that can you predict based on the available data. But then again, as I said, that those 10 experiments that you do, the quality of them becomes important to predict the rest of them. So, therefore, the databases are necessary, and the databases can be updated with new data as the research advances, making them long term tools. So, all the databases, it is not that once you made and that is it. You can always update it with the new information, new findings that are coming out. Now, what are the challenges in creating database? It requires extensive effort to collect, evaluate and optimize the data for inclusion. Inaccurate or incomplete experiment data can lead to errors in predictions, and it requires meticulous validation to ensure reliability, and developing and maintaining high quality databases require significant investment in resources and expertise. So, it is not easy to maintain data. You have to constantly keep updating it. One has to ensure that the databases contain correct data, and the complete data, then only the predictions can be reliable and more comprehensive. So, the thermodynamic database, it contains data about phases, their stability, Gibbs free energy and phase equilibrium. And these are the essential for calculating phase diagrams and understanding material stability under varying conditions. Parameters such as enthalpy, entropy, activity and phase composition, they are obtained for various temperature and composition ranges, and they are also a key part of the database. Then kinetic database, it includes information about diffusion coefficients, mobility of species and reaction kinetics, and it is useful for predicting microstructural evaluation and time dependent phase transformations. So, today I will give you a very brief example of one of the thermodynamic database. Now, what are the sources of these thermodynamic and kinetic database? So, some standardized databases, they are provided by software developers like Thermocalc, Pandat and FactSage. For example, you have TCFE, TCNI, FE is for the ferrous alloys, TCNI is for the nickel based alloy, MOB-NI is for the nickel diffusion data. Then you have the experimentally derived data, which is high temperature calorimetry experiments, where heat capacity, enthalpy and are measured. Then you have phase equilibria studies, then diffusion couple experiments for the kinetic data. So, these are the experimentally derived data which are useful for the creating a database. Then computational methods that like molecular dynamics simulations or first principle calculations, these are used to compute the thermodynamic properties such as Gibbs free energy, formation enthalpy, vibrational entropy, and molecular dynamics, it simulates atomic interactions to estimate diffusion coefficients. So, these are also the tools which provide input data. Then already done literature, where already experiments are done, sometimes you dig into those literature where you see the published experimental data and phase diagram reviews, example from ASM handbook or CALPHAD journal and other scientific journals, and or reports or thesis with detailed experimental results, they can also serve as important literature sources. And then collaborative efforts, consortia and institutes, they come together like NIST materials project and OpenKim provide curated data sets, and industrial partnerships, sometimes for some specific alloy systems, companies also contribute proprietary data so that the database can be built. So, these are the sources to create thermodynamic and kinetic databases, and with which are the reliable sources. So, one has to filter out which are to be taken, and according to the system and the need, we can take all of them or some of them. Then so let us have a look at what are the different steps that go on into the database generation. So, this methodology, as we said, it is a well established approach for predicting these properties, and it is widely utilized by several softwares, some of which we saw last video. Thermocalc, Pandat, FactSage, OpenCalphad, etc., to develop their databases. So, the key steps, as I said, are the data capture, assessment, optimization, storage and validation. So, data capture means that you gather the experimental data and the ab initio calculations. Ab initio means the first principle calculations, as I mentioned in the last slide. These refer to the DFT, molecular dynamics and other computational tools which provide you the necessary thermodynamic or kinetic data. Then assessment is the analyze and model the captured data. So, you analyze the data and model the data. Optimization is to fit thermodynamic and kinetic models to the data. Then storage is where you store the results in a thermodynamic database file, which has an extension .tdb. And validation is compare predictions with new results or the experimental results or any new data, and confirm the accuracy for practical applications. So, this is again given in a flowchart format also. So, you have the data capture, assessment, optimization, storage, validation and application. So, these are the key steps in the CALPHAD methodology to create a database. So, the step 1 is to see if you want to have a search and evaluate the available database first of all. So, for example, if I want to make a prediction for a certain alloy, then can I see what are the available databases first of all. So, that we understand the current state of knowledge for the system of interest. And then second thing is, it is important to gather which elements, which phases and properties are important for our system. Sometimes when you need the entire gamut of, you want to study the entire gamut of, let us say, interactions between two elements. You want to have the data from 0% of one element to the 100% of the other. So, in that case you may need a more exhaustive database. Sometimes you are interested in key phases. So, accordingly and then which properties, what you want to predict. So, that should be contained in the database. So, all that you should do a prior search or prior discussion to what is important for our system. So, for example, if our system of interest is COCr-Ni-Al alloy, then let us say the following considerations are essential. This is a alloy which is now called as medium entropy alloy. We have a small section, or you can right now call it as a multi-component alloy, where all are in equiatomic proportions. So, then the steps would be what you need to consider is check if there is a reliable data available for the binaries. That means cobalt, nickel, chromium, aluminum, ternary systems like COCr-Ni, Cr-Ni-Al in the existing databases. Then what are the possible phases that could exist in the system, including solid solution phases like FCC, BCC, intermetallics, Al-Ni, Al-CO, and other potential phases like oxides or carbides if impurities are relevant. So, say you are processing by a method where carbon contamination or oxygen contamination is unavoidable, then you may want to include or you may want to look for a database which contains the information about oxides and carbides in addition to these elements, so that you have the prediction about that as well. Then what are the properties that you focus on? So, let us say you want to focus on thermodynamic properties or kinetic properties or phase stability and transformation temperatures. If you want to focus on kinetic properties, you will have to choose a mobility database. So, you should first have the information as much as possible about your system, what you want. Then if you identify certain gaps and inconsistency, then the experimental data or first principle calculations may be needed to supplement and improve the database. So, say you want to analyze a particular phase, but that phase is not yet studied in the literature, it is not available in the experimental results or in any of the previous databases. Then it means there is one option that you can generate the data for that phase using some first principle calculations. So, that would also improve your database. Now, for example, in thermocalc, we talked about the thermocalc, this is what we use in our institute. So, to develop a nickel based alloys database, we have TCNI12, the following systems are assessed. So, these are the list of all these systems. So, 371 binary systems. Okay. So, this is nickel based alloys database TCNI12. So, 371 binary systems are assessed. and the ternary systems are about 431. So, various combinations are assessed, and totally around 733 solution and intermetallic phases were nearly all stable phases in all assessed binary systems, and most ternary systems are modeled. So, you can see that to create one database, how much of the effort goes into the assessment of a number of binary systems, a number of ternary systems, and then so many of the solution and the intermetallic phases and so on. Then once you have captured the data, once you have gotten the data by either experiments or by theoretical approach or by existing databases and so on, then the second step is to define the Gibbs free energy model for those phases. So, in the CALPHAD, the Gibbs energy of each phase is mathematically modeled as a function of composition, temperature and pressure. If pressure is fixed, then it is a different thing. Gibbs energy is critical in computational thermodynamics, as it determines all the thermodynamic properties of the material. This we have already seen. Initially, when we talked about the CALPHAD approach also, G is equal to G ref plus G ideal plus G access, and these are the access terms that that is contained, and where Lij are the coefficients to be fitted. So, this access free energy expression actually determines how much the solution deviates from the ideality, and the crystal structure dependence, the free energy is dependent on the crystal structure, FCC, liquid and ordered phases. So, each of these different types of phases, the models that will be used are going to be different. So, for example, in a NIAL system, let us say the phases present are FCC, B2 and liquid. This is just for simplicity. There are more phases in the NIAL system. So, for example, FCC A1, the free energy can be written as G ref plus RT XIL and XI plus XL, XAL, ln XAL plus this parameter L, NIAL into XNI XAL. This is a very simple description. Okay. So, in this, this is a access term if you can call it. Then for the B2, you can write G of B2 BCC is G ref plus L dash NIAL XNI XAL. So, because here B2 is an ordered BCC, so the configurational entropy term does not come into picture, and you have this is the free energy. So, now once you assign or once you have written the free energy expressions, then we save this up to the setup file which contains the definition of phases, functional form of Gibbs energy models, initial guesses for the coefficients, and then as I said that it is like a blueprint for the thermodynamic model which lays the groundwork for the further calculations. So, again here this is just an example where we showed that only 3 phases, but in NIAL system you have several other phases also. But let us say our interest is primarily B2, then you look for a database or your database should have the most reliable estimates for B2 and so on. Then the optimization of data is the third step. So, although the data collected in the step 1 and initial modeling is also done in step 2, these raw data often contains noise or inconsistency, and then the models might not perfectly fit for the data initially. That means, you collected all the data, then let us say in the previous slide we showed some equation for the excess free energy, you used one of the models and you try to fit the model, but because the experimental data, although you be careful in collecting this data, but by the nature of the experimental studies itself, you can get certain noise or inconsistencies, and the models initially may not fit. So, therefore, this step 3, which is the optimization of data, it ensures that the database becomes both consistent and predictive. which is essential for creating a reliable thermodynamic database file for any practical application. For example, in thermocalc, a parrot model is used, module is used for the optimization, which minimizes the difference between the experimental data and calculated results by adjusting thermodynamic parameters systematically. And optimization is performed using a weighted least squares approach to balance the different types of input data. PanDat, it uses pan optimizer module for a parameter optimization, which allows optimization of multiple types of experimental data, example phase diagrams, thermochemical data simultaneously. Then the next step is to store and validate. So, the finalized thermodynamic parameters are stored in a TDB file. This is a standardized format widely used for CALPHAD databases. It includes Gibbs energy models, interaction parameters and phase descriptions for all relevant elements and phases. So, this then serves as a ready to use database for calculations, phase diagram generations and material design simulations. And TDB files can be easily updated to incorporate new data or the improvements. And then the validation step, you compare the calculated results with the experimental data and the theoretical predictions, and then the discrepancies can be identified and the database consistency and accuracy can be assessed. And as we said, because these are database allows the updation. So, if any discrepancies are found, the corrections can also be incorporated. So, as I said, it is an iterative process. You can revisit and refine models and parameters as needed, and then you can test using independent data sets to ensure reliability and the predictive capability. So, here is just an example to give you a flavor of how the TDB file looks like. So, this TDB file is for an NISI system. This is a reference for the same. And so, you can see that this is how you will see a TDB file. The first few lines they contain general info about the authors and some comments. Okay. So, that you can see here what we mean by authors here, like the parameters are taken from. So, this is the reference paper where the parameters are taken from. Okay. So, this is, you see, this is a ab initio energetic calculations. So, here these are in ab initio calculations were utilized, then the assessment of nickel silicon system was done. So, then this is also created by this group of authors. Again, a reference is given here, and so these are created by these authors whose references are given here. Then any comments if are there, if it is present, that is also shown here. That for example, lattice stability is taken from this particular unary database, and you see there is a mistype in the table 1 as below. So, all these comments also you can mention in the TDB file, and then elements in the system, crystal structure, atomic mass, enthalpy, entropy at the standard states are also mentioned. Okay. So, for example, this contains nickel and silicon. Okay. So, this are the mentioned elements. If it contains multiple elements, then each of the element would be listed at the standard state. Then it will have the descriptions of unary elements. So, for example, you see that here in this it contains the nickel description for different crystal structures such as BCC-Ni, HCP-Ni, etc. So, here these are the various functions you can see for the free energy for BCC-Ni, for HCP-Ni. You may say that sir, Ni exists as only FCC structure, but and here the standard state is defined also as FCC. But you see that when you talk about the CALPHAD predictions or the predictions based on the free energies, it will try to calculate the nickel free energy in all these possible structures. whether it's a BCC, HCP, and then it automatically will tell you that the FCC free energy is the lowest, say let's say at the room temperature. So that is again one of the powerful nature of these predictions, because you want to have this data when you are predicting, and this kind of data you cannot obtain experimentally. I will give you a short example. For example, if you want to write the free energy for a nickel chromium system in the BCC side, that means in the chromium side. So you see that we write XAGA plus XPGB plus certain mixing terms. So now when you want to calculate XNI, GNI on the BCC side, where is the data? You because experimentally you don't have the BCC nickel available. So these are the ways in which computationally you can assess what is the free energy description, what would be the free energy description for BCCNI, and those are the informations that are contained here. Then you have a similar description for silicon. So if you have multiple elements, it will contain a description for each of the elements that are present. Then you have the description for phases and parameters. You can have additional info on magnetic ordering as well. So this is for the FCC Ni, and then here it is for the silicon. So here then you have for the phases also, for example here it is Ni3 Si. So like that you can have for various parameters are listed here in order to so this is what forms the next part of the TDB file. So this structured format, so because we saw that okay, these are the structured format, this allows easy parsing by CALPHAD software like Thermocalc, Spandat or FactSage, so that you don't have to create or modify your TDB files again and again, and this structured format allows easy parsing. Then I will like to end with just emphasizing the importance of the continuous revaluation. This is with the example of a cobalt tin phase diagram. So cobalt tin phase diagram, before 1991 the COSN3 was missing, this phase, this intermetallic phase was missing, but later discoveries confirmed its existence. So this highlights the need to revisit and reevaluate phase diagrams regularly to incorporate new data, and it ensures the accuracy and completeness of the CALPHAD databases. So this was the phase diagram. So this is a schematic generated, the original phase diagram you can refer to ASM handbook, and where the COSN3 phase you will see is not present, and whereas the updated COSN phase diagram you will see that COSN3 phase in fact in alpha and beta forms is now available. So this is what is the updated, once you have the information experimentally about COSN3, it goes into and you collect more thermodynamic information about it, it goes into the database, and then the predictive capabilities, or when the predictions start, taking that into account as well. Here are the references from which some of the information used in this slides and the data presented has been taken. We will end today's lecture, and we will now, once we have now in the last two lectures and today's lectures, we have understood more the theoretical part of the CALPHAD and the softwares, and we have seen the databases also. So to give you a flavor, we will try to solve a couple of problems using this software, so that you get a hands-on experience. Okay, so we will be using the free license ones only, so that you don't have to install anything or licensed or a commercial version. Thank you.